Hello, it's Dr. Armand again, bringing you another exciting lecture on general chemistry topics. Today we'll be talking about buffers. You may ask, well, why do I need to know about buffers? Well, buffers are important because there's a buffer in your blood that maintains the pH of the blood. I believe it's the bicarbonate carbonate buffer system. And so it helps regulate the pH of your blood. Because if your if your blood becomes too acidic, guess what? You have acidosis. If your pH becomes too basic, guess what? You have alkalosis. Your blood becomes too basic. So typically, the blood buffer likes to keep the pH within plus or minus 1 pH unit of the pKa of the weak acid in your buffer. And so today what we're going to be talking about is A, what are buffers? B, how do buffers work? And C, calculations involving buffers. So how does the pH change when we add a strong acid to a buffer? Versus how does the pH change when we add a strong base to the buffer? And so that's what the object of today's lesson is. Sit back, relax, and enjoy the chemistry. Oh, wrong folder. My bad. Let's do this again, shall we? Alrighty. That was Gen Chem 1. My apologies. So I call this Chapter 19, Part 1 lecture. And so today we're going to be on buffers. Just a little light humor before we begin. I found this joke I had a few semesters ago. So here we have two minions. One minion asked the other minion, "What do you do with a sick chemist?" Give them a popsicle. Where's Bob? If you can't heal him, you can't cure him, you might as well bury him. Just a little light joke to lighten the mood for today's lecture. Now, just a kind of practice problem involving ranking acids and bases, or acids from strongest to weakest. I know my students love to do these types of problems. So here we have a series of weak acids, and we want to rank them from strongest to weakest. So we want to see first, what is the element attached to the acidic proton? So, okay, A is attached to oxygen, B is attached to nitrogen, C is the oxygen, D is a carbon, and E is an oxygen. So you see that the acidic protons are connected to elements in the same row. So the greater the electronegativity, the stronger the acid. So right off the bat, the weakest acid would be D, be number 5, because carbon has the least electronegativity out of oxygen, nitrogen, and carbon. Then would be B, because again, oxygen has the greatest electronegativity out of oxygen, nitrogen, and carbon. So now we're left with A, C, and E. So we looked at the elements. Now we're going to go to resonance. So which one of these structures has resonance? Well, A doesn't have resonance, or very good resonance. No, it doesn't. It just has an OH. C has a carboxylate group, so it has resonance. E also has a carboxylate group, which has resonance around the reaction center. So since A doesn't have any resonance around the reaction center, any major resonance, it would be the third strongest acid out of these. So now we see that C and E have resonance. So again, we started with element. Now we go to resonance. Next one is inductive effect. So which one has a greater inductive effect? Well, you see here, C has an electron withdrawing group, chlorine, whereas E does not. So E would be the second strongest acid, followed by C, which is the strongest. And that's just a refresher on ranking acids. You should feel lucky because these are actually questions that I would post on my weekly quizzes. And actually, I'm explaining them to you free of charge. So now we get to buffers. So what are buffers? Well, buffers help lessen the impact when you have the addition of an acid or base. So if you add an acid to a solution, it won't affect the pH that much. If you add a strong base to the solution, for example, it won't affect the pH that much. It only moves within plus or minus 1 pH unit of the pKa of the weak acid in the buffer. So that's the general explanation of a buffer. It lessens the impact of it. So if you add small amounts of strong acid or small amounts of base in an unbuffered solution, you see the pH dramatically decrease or dramatically increase because there's nothing there to buffer the solution. So if our blood didn't have a buffer in it and we drank something very acidic causing our pH to drop, it would cause some serious issues. That's why our blood has a buffer. But now if we take a strong acid or a strong base and add it to a buffer solution, very small changes occur in the pH as long as the buffer is there. Now there are times when you can destroy a buffer, and we'll talk about that in a little while. But for the most part, when you add small amounts of a strong acid or strong base to a buffer solution, cause very slight changes in the pH within plus or minus usually 1 pH unit of the pKa of the weak acid in the buffer. And buffers are typically a conjugate acid-base pair. And it's usually a weak acid and its conjugate base. For example, acetic acid and the acetate ion, but this would be a buffer that may be acetic acid and sodium acetate, because sodium doesn't affect pH. Or a weak base and its conjugate acid. This example could be, for example, NH3 and NH4Cl. That's an example of a weak base and its conjugate acid. But regardless, it's dealing with weak acids and weak bases. So if you just have a strong acid and a strong base, it's not going to be a buffer. Or if you have a neutral salt, it will not be a buffer. And so buffers work through what's called the common ion effect. And this will be the main theme for the chapter 19, especially when we get into KSB. So a common ion effect occurs when you already have a common ion in solution and you add more of that ion, is going to shift in a way so that equilibrium is going to shift in a way to keep it from forming. So for example, if we have a solution of 0.1 molar sodium hydroxide and we want to dissolve silver chloride in it, well, there will be less silver chloride that will dissolve in a solution of sodium chloride because there's already chloride present. So this will prevent any more or a lot of silver chloride to be soluble. So it'd be silver chloride would be less soluble in 0.1 molar sodium chloride than it would be in water because it already has a common ion in solution, which will inhibit the dissociation of silver chloride. So in a buffer, say we have acetic acid and acetate, and this is again back to that famous word that everyone likes, Le Chatelier's principle. So we're mainly focusing on the hydronium ion in it. So if we add more acetate, it's going to shift to make more acetic acid to maintain this equilibrium. Now if we add a strong acid, say we add some H3O plus, When we add H3O plus, we're increasing the concentration of H3O plus, so it's going to shift to make more acetic acid. So the concentration of acetic acid goes up, the concentration of your weak base goes down. Because again, as you add more H3O plus, you're going to increase the concentration of a product. It's going to shift to make more reactants and decrease the products. Now, if we add, for example, hydroxide, if we add a strong base to a buffer, a strong base is going to react with H3O plus, decreasing its concentration. And then since you're removing a product, the equilibrium is going to shift to the right to make more product. So this is going to increase. The amount of weak base increases, the amount of weak acid decreases. And that's how a buffer works with strong acid and bases. Now the common ion inhibits the dissociation of the weak acid. So if we already have a solution that has some weak base in it, it's going to prevent some of the weak acid from dissociating and forming weak base. So for example, if we have a 0.1 molar solution of acetic acid and no acetate, well, 1.3% of the acetic acid will dissociate. But now if we increase the concentration of acetate to 0.05, you see less of the acetic acid gets dissociated because there's already a common ion in solution. And as we increase the concentration of the weak base, you see a decrease in the amount of weak acid that gets dissociated. So when you have a buffer, since you already have weak base in solution, very little of the weak acid is going to be dissociated. And you see that the pH increases because less weak acid is being dissociated to produce hydronium ions. So if you have a large amount of weak acid and weak base, they will consume small amounts of hydroxide and hydronium ion respectively. So again, we have this equilibrium equation. As we add a strong acid, if we add H3O plus, we'll come back to that. Not that right now. And so this is the Ka expression of the buffer. So Ka is the conjugate base over or times H3O plus over the conjugate acid. Now we can rearrange this to solve for the concentration of H3O plus. And so if we know the Ka, we know the concentration of weak acid and weak base, we can indirectly calculate the pH. And so the hydronium ion concentration depends on the ratio of weak base and weak acid. If there's more weak acid than weak base, that means there's more weak acid in solution. The pH means there's more H3O plus, so the pH decreases. So pH decreases. Now, if the ratio of weak acid to weak base goes down, that means you have less H3O plus in solution, then that means the pH increases. So if you have more weak acid than weak base, the pH will be usually less than the pKa. So we have more concentration of weak acid than weak base. then pH will decrease. Typically, it'll be less than, I won't get to that. And then if you have more, and the reason it will is because we're satisfying this ratio up here. So Ka times the concentration of weak acid over weak base will affect the amount of H3O plus in solution. So how does a strong acid react with a weak base? So there are two things you can do to a buffer. You can add a strong acid and you can add a strong base. So when you add a strong acid, when you add a strong acid, you're increasing the amount of hydronium ion. That means Le Chatelier's principle says, hey, we're going to consume some of the products to make more weak acid. So the concentration of weak base goes down, the concentration of weak acid goes up. And so your pH will decrease. Now, if we add a strong base, when we add a strong base, we're going to decrease when we add a strong base, we're going to decrease the amount of hydronium ions in solution. So therefore, the weak acid will react with the strong base to form more weak base. And the weak acid decreases. Because remember, the dissociation is a two-step process. So we have weak acid, so that's the first step. Second step, we get that. So again, as you increase the concentration, as you add strong base, this is going to decrease. So when this decreases, you're going to shift to make more weak base and H3O plus, and that's going to decrease the concentration of weak acid and increase the concentration of weak base. So a strong base reacts with the weak acid component. A strong acid acts with the weak base component of a buffer. So let's take a look here. Which of the following equal molar pairs would form buffers? So equal molar means they're the same concentration. We want to form a buffer solution. So typically a buffer is a weak acid and conjugate base. So a buffer consists of a weak acid and a conjugate base. So let's go through these. Is NaCl a weak acid? No. Is HCl a weak acid? No. HCl is a strong acid. NaCl is a salt solution, but it doesn't come from a weak base. So this would not form a buffer. Is NH4Cl, is that a weak acid? Well, NH4 plus is a weak acid, and NH3 is its conjugate base. So that would form a buffer. HNO3, is that a weak acid? No. And KNO3 is not a weak base conjugate base. Next we have acetic acid. Is acetic acid a weak acid? The answer is yes. Is NaOH a weak conjugate base? The answer is no. So this one would not be a buffer. Because these are equal molar concentrations. Remember that. These are equal molar pairs. Now we have sodium bicarbonate. It's a weak acid. Is sodium carbonate the conjugate base of that weak acid? It is correct. This can be a buffer. HCl, is that a weak acid? No. So this cannot be a buffer. Because again, it's equal molar pairs. So B and E were the correct answers. So now we want to see which one of these can be a buffer, and we give different concentrations. So let's take a look at this. We have 0.2 molar HCl and 0.15 molar sodium nitrite. But since the concentration of strong acid is greater than the concentration of weak base, this would not be a buffer. No. Next we have 0.1 molar CH3NH plus and 0.2 molar CH3N. So T-butylamine and T-butyl ammonium cation. Is this a buffer? Yes, because they contain a weak acid and its conjugate base. 0.1 molar HBr and 0.1 molar KBr. Is this a buffer? The answer is no, because they're both, one is a strong acid, the other one is a neutral salt. Next we have 0.15 molar carbonic acid, 0.1 molar strontium hydroxide. Will this form a buffer? The answer is yes, because the concentration of weak acid is greater than the concentration of strong base. So this will actually form the following buffer. So it'd be 0.05 molar H2CO3 and 0.1 molar HCO3 minus. So this would be a buffer. So far we have B and D. Next we have 0.3 molar benzoic acid and 0.05 molar potassium benzoate. The benzoic acid is a weak acid, benzoate is its weak base, so this would form a buffer. Next we have 0.05 molar HClO4, 0.15 molar KClO4. This is a strong acid and it's neutral conjugate base, so this would not be a buffer. So the buffers are B, D, and E. So now what we're going to do is we're going to help simplify this Ka expression for a buffer, which is H3O plus times A, the conjugate base concentration, divided by the conjugate acid concentration. And what we're going to do is we're going to take the negative log of H3O plus equals the negative log of Ka minus log of Ha over A minus. And what we get is the equation that helps us determine the pH of a buffer, the Henderson-Hasselbalch equation. So pH equals the pKa plus the log of the concentration of weak base over the weak acid. And this is the equation we're going to use to calculate the pH of buffer systems. So make sure you remember this equation. So here we have a buffer composed of 0.05 molar HClO and 0.04 molar NaClO, so sodium hypochlorite. How will the pH of this buffer be affected if we add 1 gram of HCl to 500 milliliters of this buffer? So first what we need to do is let's determine the moles of HCl. 1 divided by 36.5. So that's the moles of HCl. Now let's calculate the moles of sodium or hypochlorite, because that's the weak base. Oop, made a boo-boo. Let's do this. So notice here, notice that the moles of weak base is less than the moles of strong acid. So what this means is that this buffer is going to be destroyed, so the pH would decrease drastically. Because that strong acid is going to consume all the weak base, and then there's going to be some strong acid left over, so that's going to cause the pH to drop drastically. So you got to look at moles and moles. So now, we have a buffer solution consisting of 0.35 molar propanoic acid and 0.25 molar sodium propionate. We want to know what's the initial pH of the buffer. And we have that pH equals the pKa plus log of concentration of base over acid. The base is typically the one with the group 1, usually it's a group 1 cation, when you have the other one is H. So again, this is the weak acid, this is the weak base. We have the Ka, but you see for Henderson-Hasselbalch, we need the pK. So the first thing we need to do, determine the pK. So the pKa is 4.82. So now, to determine the initial pH, all we do is we put in the pKa plus log of concentration of base divided by concentration of acid. Now, since the acid is greater, the weak acid is greater in concentration than the weak base, the pH will be less than the pKa. And we get about 4.67. So that's the initial pH of this buffer. Next, we want to know what's the pH of the buffer after we add 1.1 grams of HCl is added to 1 liter of the buffer. So what we have to remember here is that when you add an acid, it's going to react with the weak base. So CH2 plus H3O plus. Oh. Excuse me, that's butanoic acid and sodium butanate. I apologize, I made a correction. It's butanoic acid and sodium butanate. CH3, CH2, CH2, COOH plus H2O, OH, H2O. So this is the reaction. So again, since we're adding a strong acid, it's going to react with the weak base. So now we're going to use our ice table. So we have initial, change, equilibrium. And since we're using 1 liter, the moles equal the concentration. So let's first find the moles of HCl. So moles of HCl equals 1.1 divided by 36.5. So the moles of HCl equal 0.0301. So initially we have 0.0301 moles of H3O plus. Since it's 1 liter, we have 0.25 moles of our conjugate base and 0.35 moles of the conjugate acid. Again, we can do this because we're doing 1 liter. If it was other than 1 liter, we'd have to find the moles of each conjugate acid and conjugate base and then do the calculation. So the change, all the strong acids going to react with the weak base. And then we're going to add it to the weak acid. So what's going to happen? All the strong acid is going to react with the conjugate base to form weak acid. So the concentration of weak acid goes up, the concentration of weak base goes down. So at equilibrium, at 0.22, 0, that. Now pay attention here, because if this was actually not 0, let's say it was some left over, that means your buffer is destroyed. So the moles of strong acid should always be 0. If it's not, that means your buffer was destroyed, and you just find the concentration of strong acid and then determine the pH. So now we have the resulting concentration of weak acid and weak base, because again it's 1 liter, so we can determine the pH. pH equals 4.82 plus log of base divided by acid. And it should be less than 4.67 because we added more acid to it. And we get 4.58. And that's the pH of this buffer after 1.1 grams was added. Now moving on to C, we want to know, this is independent of part B, we want to know if we take that original buffer and add 0.95 grams of sodium hydroxide, what is the pH of the buffer? So again, since we're adding a strong base, it's going to react with the butanoic acid. To form more conjugate base as product. Before we begin, let's find the moles of sodium hydroxide, or sodium hydroxide, I should say. Now, since this is not 1 liter, this is 500 milliliters, we need to find the concentration of, we need to find the moles of weak acid, which would be 0.35 times 0.5, and the moles of weak base. So now we have the moles of weak acid, moles of weak base. We can do our ice table. So we have the initial, change, equilibrium. So initially, we have those concentrations. The change, all the strong base is going to react with the weak acid to form weak base. So at equilibrium, now we get the moles of weak acid and weak base. We need to find the concentrations. And again, I like using moles. Some may say they use concentration. I like doing the moles and then reconverting it back to concentration. And we find the concentration of weak base. And you'll see here that the concentrations are fairly almost the same. So this pH is going to be near the pKa. Get 4.81, so almost the pKa. So again, if the moles of strong base were not zero, that tells you that the buffer was destroyed. So then you just find the concentration of hydroxide, find the POH, and then you can find the pH. So oh, I actually had them. My bad. All right. So now we have a buffer, a 1 liter buffer containing 0.15 molar of chlorous acid and 0.3 molar of sodium chloride. What is the pH after 0.15 molars of HCl is added to the buffer? And it gives us the Ka of chlorous acid. And this is strong weak acid. This is a Ka of 1.1 times 10 negative 2. So again, since we're dealing with buffers, we're going to be using the Henderson-Hasselbalch equation, pH equals pKa plus log of base over acid. Be careful when you Google this equation because sometimes it may say pH equals pKa minus log of concentration of acid over base. So the plus log means base is on top, acid is on the bottom. And so since we're dealing with Henderson-Hasselbalch, we need the pKa. So you take the negative log of the Ka, gives you the pKa is 1.96. We need our equation. So since we're adding a strong acid, it's going to react with the weak base and form weak acid. So now we can, and since we're dealing with 1 liter of solution, the molarities are the same as moles. So we have 0.15 moles of chlorous acid and 0.3 moles of sodium hypochlorite. So we do our initial, change, equilibrium. So initially, 0.35 moles of the weak base, or excuse not 0.35, 0.3 moles of the weak base. We're going to add 0.15 moles of strong acid, and we have 0.15 moles of weak acid. So the change, well, all the strong acids going to react with the weak base and going to be added to the weak acid. So then we have so notice again here that all the strong acid gets consumed. So our buffer is not destroyed. So since this is 1 liter, this equals the concentration. So we have pH equals 1.96 plus log of weak base divided by log of concentration of weak acid. And since the weak acid is greater than the concentration of weak base, our pH will be less than the pKa. And we get 1.66. And that's the pH of this buffer. Again, strong acid reacts with the weak base. Now we want to calculate the pH of a buffer consisting of 0.35 molar HF, 0.25 molar potassium fluoride after the addition of 5.75 grams of KOH to a 500 milliliter buffer. So again, we're using the Henderson-Hasselbalch equation. We need the pKa. So for HF, it's 3.17, a modestly strong weak acid. And we need the reaction. So since we're adding a strong base, it's going to react with the weak acid to form weak base. So since we're given mass, we have to determine the moles of potassium hydroxide, which equal the moles of hydroxide, because it's 1-to-1. .75 divided by 56.1. 0.102. So that's the moles of hydroxide. Since we're dealing with 500 milliliters, we've got to find the moles of weak acid. Again, I like using moles because we're going to need moles in titrations. And then we need moles of fluoride, which is equal to the moles of sodium fluoride, or excuse me, in this case, potassium fluoride. So now we have the moles of strong base, weak acid, and weak base. We can do our ice table. So initial, change, and end. There we go. So initially we have 0.175 moles of weak acid, 0.102 moles of strong base, and 0.125 moles of weak base. Change minus 0.102 minus 0.102 plus 0.102. So all the strong base is going to react with the weak acid to form that much weak base. And so we get so again, these are moles of weak acid and weak base, and now we got to find the new concentration of HF, which is 0.073 divided by 0.5, and fluoride, which is 0.227 divided by 0.5. 0.146. Excuse me, that's this one. And then the other one, 0.454. So now we have the concentrations. We can calculate the pH. pH equals 3.17 plus log of concentration of base divided by acid. And again, since the concentration of weak base is greater than the concentration of weak acid, our pH should be above the pKa. So it's going to be 3.66, and that's the pH of this solution, of this buffer solution, after 5.75 grams of potassium hydroxide was added to 500 milliliters of this buffer. And then one last problem. We want to calculate the pH of a buffer consisting of, again, 0.35 molar of HF, 0.25 molar of KF, and this time we're going to add 10 grams of potassium hydroxide. So again, we're dealing with the Henderson-Hasselbalch equation because it's a buffer. pKa, negative log of Ka, 3.17, and our reaction scheme. So again, since we're dealing with 500 milliliters of buffer, we need to determine the moles, the moles of hydroxide. Again, moles of hydroxide equal moles of sodium hydroxide, or what is this? Yes, potassium hydroxide, which equals 10 divided by 56.1. 0.178. That's the moles of hydroxide. Now we find the moles of weak acid. And we find the moles of weak base, which equal the moles of potassium fluoride, which equal 0.175, 0.125. So now we're ready for our ice initial change end. So initially, we had 0.175 moles of weak acid. We added 0.178 moles of weak base, or excuse me, strong base. We added 0.178 moles of strong base, and we started with 0.125 moles of weak base. So notice here that the amount of hydroxide is greater than weak acid, so we're going to subtract 1.75 from the hydroxide. Again, we're doing this because hydroxide is greater than weak acid, so we're going to subtract the weak acid. from the hydroxide. So now we get 0 weak acid, 0.003 left of the strong base, and 0.3 moles of weak base. So again, now we have to notice something. So we have an excess of strong base left. So what we're going to do is we're going to find the concentration of hydroxide, then find its pOH, and then find the pH, because now the buffer has been destroyed because we have an excess of hydroxide ions. So concentration of hydroxide equals 0.003 divided by 0.5. 0.006. Now we find the pOH. .22, but don't stop here. Then we got to find the pH. .11.8. It's not 11.8. 11.82. No, 11.8. 11.78, my bad. And so that's the pH of this solution. So you see that the pH, this buffer has been destroyed because the pH increased drastically, because all the weak acid was consumed and we had leftover strong base in solution. So then we found the concentration of this strong base, found the pOH, and then found the pH. So that concludes today's lecture over what are buffers, how can we identify what types of mixtures are buffers, calculating the pH of buffer solutions, calculating the pH of a buffer after you added a strong acid and a strong base. So again, it comes back to the Henderson-Hasselbalch equation. You always need the pKa and the concentration of weak acid and weak base to calculate the pH of a buffer. So I hope today's lecture was informative and that you learned something. If you did learn something, make sure to hit the like button, or if you enjoyed today's lecture, hit the like button as well. I always recommend that you watch these videos more than once, so that way you watch it once, and then the second time you watch it, pause it, do the calculation, see if you get what I get, and then you can check your work. So that's it for this session. This is Dr. Armand signing off.